Okay, so good evening everyone and welcome to the ninth session of the course Dynamical System and Control. So today we will be mainly discussing about the feedback control and how it plays role in giving stability of an unstable system. Okay. So that's all we'll see. So let us recall the concept of stability what we have already seen earlier. So this consider this linear system where A is n cross n matrix, y is a vector in Rn and y prime is the derivative. So this is the linear system that we have and this is the initial data. So if you consider the eigenvalue, so stability of this whole system is determined by the eigenvalues of this matrix A. Okay, so that can be characterized using eigenvalues of A, the stability. And so here you consider this sigma. We define sigma as the maximum of real part of the eigenvalue. So this means the real part of lambda, where lambda is eigenvalue of this matrix A. So define it as a sigma, the maximum of them. Then if you have any omega, if you take any omega greater than sigma, then there will exist a constant C such that this exponential of the matrix A will satisfy this inequality. So you will get a bound on the exponential matrix, and this is nothing but the solution. So we know that the solution of this system is given by yt equals e raised to the power at times y0, right? So this is the solution of this linear system. So over here, this if we get the bound on this exponential term, we'll get the bound on the solution, and that's what it's written. So if you have any omega which is greater than the maximum of the eigenvalues, then you have this estimate, which is the norm of the solution will be given by exponential of omega t times the norm of initial data. So this is the estimate what we have. Now if your sigma, okay, if sigma is less than 0, okay, so suppose this is 0, this is sigma, then obviously you can find some omega over here which is negative. So this you will get here omega which is negative right? So as t goes to infinity, this term will go to 0 as t goes to infinity, correct? So the norm of the solution yt is converging to 0. Okay, so that means this yt solution is converging to the equilibrium solution y is equal to 0. And this, okay, so this is the case when sigma is less than 0. Okay, so this is the case when the maximum of the eigenvalues of A is less than 0, then we have such asymptotic behavior, which is that the solution is going to 0 for large time, correct? So this kind of stability is called asymptotic stability, that we have already seen. Now the question is, suppose this matrix A, what we consider, does not have this property, that is the maximum eigenvalues is either 0 or greater than 0. Okay, so non-negative. If the eigenvalues are non-negative, then that is not stable. So our goal would be to add some term here, okay, with this, which will be the control what we can provide to the system. And the question would be, can we give some input or control so that the resulting system will be stable? Okay, so that is called stabilizability. So we have studied controllability, where we control the trajectory from one point to other. Now this notion is stabilizability, which is you want to stabilize an unstable system. Okay, so before going to that, let us see. So I haven't proved how this estimate is true, this one, okay, but I'll try to show you using example, okay, that how this estimate can be expected. Okay. Then we'll come to stabilizability. So suppose you have this A. Now you already know what is the exponential of this matrix. The exponential of this EAT will be given by e raised to the power minus 2t, then 0, 0, e minus t. Right? This is the exponential of AT, where the A matrix is given by this diagonal. Right? In this case, you can see that the norm of EAT, if you want to calculate, what it will be just you do a square of all the entries. So here you will get E minus 4t plus E minus 2t. Correct? This is what we get. Now you can bound it obviously by 2 times you dominate this e raised to the power minus 4t by e raised to the power minus 2t. So we'll ultimately get this thing. Now I can just separate this root 2 and then I'll have my e minus t. Okay, so we'll have this entry that it is root 2 times exponential of minus t. Okay, so we have got an estimate of this kind, what we mentioned over here, what we saw here, right? So over here you see what is the power, over here what is the omega, if you compare with this one. Okay, here omega you can see is minus 1. Okay, so let's not worry about this constant c. Then we can say, and let us consider what is the sigma, which is the maximum of real part of the eigenvalues lambda is an eigenvalue of A. So if I consider this sigma would be maximum of, this is minus 1 and minus 2. These are the eigenvalues. So the maximum is minus 1, right? So over here what we are saying that the sigma is equal to omega in this case, right? So here looking at this, so let me point it out here. So over here what I'm saying is that omega is equal to minus 1 and over here the sigma is also minus 1. So in this particular case we have omega is equal to sigma. That means, okay, why I'm emphasizing this, because this omega is something that decay rate. Okay, so suppose you have this yt, suppose you have some ft, let's not go, so ft less than equal to e minus t, and there is another function gt which is less than e minus 2t. So over here both of them goes to 0 as t goes to infinity. The point is this one goes faster, right? So the maximum power you get, the better you, I mean not the better, but this would be called the better decay rate, that it is decaying faster. So the solution is converging to the equilibrium point faster in this particular scenario. So this power, maximum power, okay, what you can get is called the this decay rate. Okay, so maximum of this positive value I'm saying. Okay, so in this case, suppose in this particular case you can say that the decay rate of g, or g decays as an exponential function of minus 2 power, or you can say that the decay rate is equal to minus 2. Okay, or if you are saying decay, you just mention 2. Decay itself means that it will be minus. Okay, so this decays faster. So that's why this omega is something that we are worried about. Okay, because this, if omega is equal to sigma, then that is much better. Right? Sigma is the maximum. You are saying that for every omega greater than sigma, omega cannot be equal to sigma. I mean, it may be, may not be. So over here, what we are saying that if omega is greater than sigma, then we have this kind of bound. So for any omega which is greater than the maximum value of the eigenvalues, you will get this kind of estimate for any omega you choose. In this particular case, we are getting that both are equal, and which is much better. I mean, this is the maximum what you can get. So if you take omega which is greater than sigma, let's say 0.5, okay, I mean minus 0.5. In this case, suppose this is the bound. If you get, I mean, let's say f not e t, then e minus 0.5t, then this is a bad decay. I mean, over here, not bad. Let's say if you are getting this kind of thing, this is always true, right? When you are saying this, you can dominate this by e minus 0.5t. Okay, you can always do that. dominate it, but this is the best one. I mean, this is anyway better than this decay. So that is why this maximum values, this sometimes called the decay rate, that if you get any omega greater than this, then you will achieve this kind of estimate. So the decay rate is greater than this sigma, you can achieve that decay. Okay, over here we have seen that okay, omega is equal to sigma, but in the next example, if you see, you cannot get omega is equal to sigma, and that I will just explain. So suppose over here if you see, let me take it here. So over here if you see that sigma, if you calculate, is again -1, because the eigenvalues of A are -1 comma -1. Okay, so the maximum eigenvalue is -1. Now let us try to look at what is the exponential of this matrix. Okay, so this you can clearly see, this is A is nothing but -I plus n, and you know that this nilpotent matrix, n is the nilpotent matrix, 0 1 0 0, correct? So you, and these two can be multiplied, so they are commutative. So E of AT would be given by E of minus IT, which is minus T times I, and then e raised to the power nt, right? So you'll get E minus T plus ENT. If you do, you will just get I plus NT, because n square onward it will be 0. So you'll get 1T0 1. This is the matrix what you get. So here identity. So overall I can write it as what it would be, sorry, this would be into okay. So this would be E minus T, E minus T, T E minus T, and then here 0, here E minus T. Okay, so this is the matrix. So I'll just, so let us try to calculate this again, the norm of exponential. So let us see that. So EAT, if I do, what I'll get is, I'll just take again the same norm, Euclidean norm. So I'll get e raised to the power minus 2t plus t square e minus 2t, and then again 0, and then this 2. So I can write here 2. Okay. Now again, if you see here, this is something which is, I have to dominate this by some exponential power. Okay, so you note this fact. Let me make it smaller. Okay. Okay, so now you remark over here that if you take any power of negative power, so let's say okay, or if you take some epsilon times t, then you know that this is always greater than equal to the square of this number. So epsilon square, let us take 2, I think that would be easier. Then I will get here 4 t square by 2, so I'll get 2 overall. Right, this I am just writing this from the power series, this we have. So what I can write is that t square, I can dominate it by 1 by 2 epsilon square, and then I'll have e 2 epsilon t. Okay, so this is possible for any epsilon, greater than 0. Okay, this is what we have. So over here I can write this as, so then I can take some c. Okay, so as of now let us write properly e minus 2t, and then t square I can write it as plus some c. Let me write it here. So this is 2 e minus 2t plus half epsilon square, and then e, we can write minus 2 plus epsilon, or epsilon minus 2 t plus 2 epsilon t, correct? So this is what I have. So again I can dominate this by this term, that I can always do, because 1 is always less than equal to exponential of 2et, so that's not a problem. So what I can, combiningly I can say that it is c times, if I take the root out if I take the exponential from the root, then what I get is e minus t plus epsilon t. So I can write minus 1 plus epsilon t. Correct? So this is the norm of this matrix. So over here you see this omega can never be minus 1. So omega can never be equal to the sigma. Right? In this case, omega is not going to be equal to this sigma over here, because this epsilon is important to remove this t square. Okay, so when the matrix is diagonal, as in this case, you can get omega is equal to sigma. That is the maximum decay rate. What you can expect is the maximum of the eigenvalues. But in this case, which is written in Jordan canonical form over here, then in this case you will get this kind of term. So over here you can say that sigma omega is strictly greater than sigma. Okay, so this was about the decay rate and some examples.
Here the norm how we are defining?
Norm, okay, you can consider this as this norm. So I am taking Euclidean in the sense that suppose you have m cross n matrix, then I consider this as a vector in Rn plus m, right? Over here this is 2 cross 2 matrix, so I can consider this as a vector in R4.
You are just taking the square of all.
Correct. Euclidean norm.
Okay.
So this.
But norm. Here, what is the significance of finding this omega?
Finding this
omega.
No, it's I am saying that when I am writing this theorem, okay, so this is one theorem that you take this maximum of the eigenvalues, okay, then you can expect the decay rate or this kind of estimate. Let's not call as a decay rate as of now. So if you have sigma as the maximum value, then for any omega you have this kind of estimate. Okay, now you see this E80 norm, if it is like this C omega t, then I can, from here I cannot say, I mean this is your omega and this is your sigma. Okay, now suppose I am talking about the stability kind of thing, so this is your 0. So I mean that these are negative. Okay, if instead of omega if I write sigma, okay, then obviously this is true. So what I am saying, that this theorem, what it tells, that you cannot achieve the maximum, you need not, it does not say you cannot, but it says that it is not necessary that you will achieve this decay, which is a better one, right? Getting this one is better, because this is always, you can get this one from the here. So that's why this is a better estimate. So this theorem is telling you that you cannot achieve the maximum of the eigenvalues, but any number greater than that you can do.
Okay, that means we cannot go higher than the eigenvalue. Decay rate cannot be greater than this eigenvalue.
I mean, decay rate basically means when these constants are negative. Okay, so I am saying that the maximum eigenvalues would be a better decay rate if you choose the maximum one, but it need not be. This theorem is not telling you this will happen. But when you have a diagonal scenario, okay, like this, then this estimate, in this estimate you can see that this is maximum is over here, the maximum of eigenvalues is -1, and here you are getting the norm as in the powers of -1. So that's just a remark. So I didn't give the proof of this theorem, okay, but this is the proof. I would say that at least for 2 cross 2 matrix you can write what, if you, for any general matrix you write it in a Jordan canonical form, and then you will see in the proof that you will have this kind of power, okay, this kind of thing will come, and then you can dominate by this kind of epsilon business, and then you can say this kind of result for omega greater than sigma. So I mean this is some kind of proof. So I just did it in a very small special case, just 2 cross 2 matrix, but it can be extended for any dimension. Yeah. Any question? Okay. Okay, so this was about the stability. Okay, and now I'll talk about stabilizability. So now consider this system y prime equal to ay. This is not stable. Okay, suppose this is not true, then in that case what we do, we put something, okay, and then we try to say that this, again, the resulting system is stable. Okay, now to do that, what I want is that this u can be written in, so see, this is, let me just mention the order. So this is n cross n, and this is y is a vector in Rn, n cross 1. So this is a vector in Rn, correct? This is n cross m, and this u, I'm saying that suppose this u is written in this form, where it's m cross n and then this y, n cross 1. Okay, then again, if u, so I'm just talking about this u, if u is of this form, now you can see this is a vector in Rm, where this u should belong. So u should be in from Rm, right? So I'm saying if I can find this u in this form, okay, special, you see this u is given in terms of y, so that's what why it is called feedback. Feedback means from the state only you are getting the expression of the control. Okay, so you are not doing anything from outside, it's just from the system, you have made some change in the system so that it happens. Okay, so this kind of thing, if you write from here the resulting thing, it's like a plus bk times yt. This would be the resulting system. Now we have studied here that how to talk about how to do this kind of study, the stability of this kind of system, linear system. Okay, so we are using the eigenvalues. So over here the eigenvalues of a were not negative. If they were negative, then that system would be stable, but this is not, all the eigenvalues are negative. So what we do, we try to find this k, okay, which is in the, I mean, in terms of control, so that this a plus bk has negative eigenvalues. If it happens, then this resulting system, then the resulting system y prime equals a plus bky, this would be stable, right? And how did it become stable? By adding control of this form. So when I choose control of this form, where you can clearly see this k is not known to you, this is something that you need to find. That means that you have to find the control. So you find the control in such a manner so that this k, when multiplied with b and then added with a, has negative eigenvalues. And this is something which was already discussed a bit in the last session, right? So this is something called pole shifting theorem. That poles means basically the eigenvalues. So you have eigenvalues of a which is not as per your desire. So you do this kind of k multiplication, then this resulting matrix has the eigenvalues what you wanted initially. Okay, so this is called, you have some set of eigenvalues, now you are shifting it according to your wish. So can you do that or not? That is the question. So this is the question of stabilizability. So your system is not stable, so you want to stabilize it using some control and feedback control. Okay, so this would be the question. So at first we'll see how is this possible. So I'll state the theorem which talks about the shifting of the eigenvalues. Okay. Before going to that, let us see again some example, a very easy example. So suppose this is the system and you know the eigenvalues of this system, I mean this matrix is 1 and 2. So clearly these are not negative. So the maximum, if I take, maximum is 2, which is greater than 0. So this system is not stable, right? Okay, so what we do, so our goal would be that these eigenvalues should become negative. Okay, so what we do, we just act. So over here this B is the identity operator, so here n is equal to m is equal to 2. Okay, so just to make you understand, I am taking very basic system. Okay, with m equals to n, so we have this kind of system. Now you can see this resulting system, I can write it as y1 prime t y2 prime t, as I can write this y1 t plus u1, and then you have 2 y1 t plus u2, right? What you wanted, that your resulting system, the goal is to bring it in the system of something like alpha, okay, minus alpha 0 0 minus beta, this kind of thing, so that the eigenvalues of this matrix would be, I mean, you want to shift it to the negative real value. So over here alpha beta is positive, so you want to shift it in negative side, and I mean this alpha beta, whatever you choose, accordingly the matrix K will change, right? So I want this alpha and beta. So let us see from here, that over here looking at, so my goal would be to get here this minus alpha times y1 minus beta times y2. This is my goal from here, this is what I'm saying, right? Looking at, so this is my a plus bk. Okay, so this is my goal. So you can clearly see when you equate this and this, so what you get is u1 is minus y1 and minus alpha y1, so that y1 will cancel with this y1 and you will get minus alpha y1, and y2 is minus 2y2 minus beta y2. So this is the set of control, and you can see over here, if I want to write it in the form of a plus bk, I can say that this u1 u2 is so k times some y. So what is k? So this k would be minus 1 minus alpha 0 0 minus 2 minus beta, this times y. So maybe I should write here u1 u2 is minus 1 minus alpha 0 0 minus 2 minus beta times y, right? y1 y2, correct? So when you, so this is your matrix K, so this is K. Okay, so in this particular case we can clearly see that how to calculate this K. It was very easy task because everything was very diagonal, in diagonal scenario, and it's very easy to handle such cases, right? So our goal would be, can you hear me? I think my slides are not shifting properly.
Yeah, you are audible too.
Is it lagging, or is everything going with the same speed?
At present, I am not seeing any lag.
Okay, then maybe it is problem from my side. Okay. So now is the slide changing properly?
No, but it has not changed.
Yeah, that's what I'm
The
saying.
same slide.
I think it's lagging somehow. Oh,
Now actually,
just a second. Okay, now I think everything is fine. Okay. Yeah, so what I was saying, that in this case it was very easy to find this matrix K. Okay, now we'll develop some theory that when such steps are possible, that when can we follow some steps to get this matrix K. Okay, so let us talk when m is equal to 1. Okay, so we'll consider when you just have just one control. Okay, so m is equal to 1 in that case. So the matrix would be something like this, I mean the system. So ay plus this would be a vector, so this is n cross m, so which is n cross 1. Okay, so that means you will get some this kind of thing, b1 b2 till bn, and then you will have this ut. Now ut is in R. So this about this scenario I am talking. Okay, so this is a simpler one. Okay. So in this case our goal would be this, to prove, so my goal would be to do a stabilization using feedback control, and in that I'll be using this theorem. Okay, such thing exists, and how there are some steps to find this k, we'll come to that. Okay, so the proof of this theorem is a very constructive proof which actually gives you this k in this case, in case m equal to 1. Okay, so we'll not go into the proof, but what we'll do is we'll try to understand through an example, and then that would be enough to consider for our case. Okay. And proof already has been done in the lecture probably, so you can see the proof from there. Okay, now let's come back to this. So again, this is the same thing what I have written here. So you want this kind of control which is given in terms of the state, so u should be in terms of y. Okay. Okay, so this is the theorem that suppose you have a set of eigenvalue or set of real numbers, not eigenvalues. Okay, some n number of items you have, and your system, this one, is controllable. Okay, so over here this b is a vector in Rn. So this b is a vector in Rn. So this is controllable, suppose. Then what you can do, you can always find such matrix K which is 1 cross n, okay, such that this A plus Bk, the eigenvalues, would coincide with the set S. So what I was telling you earlier, that when can we find this K and all to make the matrix stable, what you need is the controllability. So if you have controllability of this matrix, this system, if you have controllability, then see, controllability does not gives you feedback control. Controllability just gives you that, okay, you have some rank condition, or it says you that, okay, you can move from one point to other point. Okay, so that is possible, but it does not tell you that it will be of this form, k times y. It does not tell you. Okay, so the theorem is telling you can find control in this manner, okay, u, such that this eigenvalues of a plus bk will coincide with s, and this will obviously help in getting the stability, right? So suppose the eigenvalues of a are not negative, okay, so you want some desired s, so you want s to construct some set s, okay, with negative eigenvalues, with negative entries. Then you know that you can find k such that this will have the eigenvalues of this, whatever the elements are present in the set S, and then you will conclude that the resulting system, which is y prime equals a plus bk, is stable. So you have stabilized y prime equal to ay by adding u equal to ky. Okay, so this will obviously help us in understanding the stabilizability property. So if you have controllability, then you will have a stabilizability, and in fact the decay rate, okay, you see now everything is in your hand, this S is in your hand, hence the resulting system will have eigenvalues which is given by you. So now you can achieve whatever decay you want. So this is called complete stabilizability. Okay, that whatever real number you choose, or more specifically whatever negative real number you choose, you can get this exponential of the solution. The estimate will be given as c times e raised to the power minus omega t, where omega is any number, whatever number you want you can choose, because this set S is in your hand, and hence this eigenvalues of this system is in your hand, and hence the decay is in your hand. Okay, so this is called complete stabilizability, this kind of stabilization. Okay, so over here this theorem is telling you that if the system is controllable, then it is complete stabilizable by some feedback control. Okay, keep it here. Okay, now let us come to this question. So over here you have this kind of system where the matrix A and B are given by this. And again the question is to find a matrix K such that this matrix have eigenvalues -2 and -3. Okay, so you have to prove this. So basically you have to find the control, or in other words you have to find the matrix K. Okay, and there is a process of finding this matrix K. We will follow that algorithm which is coming from the proof to get this matrix K. Okay. Okay, so over here you can clearly see that this, if you consider y prime equal to ay, then this is not stable. So you are somehow because the eigenvalues are 2 and 5, right? Eigenvalues are 2, 5. So now what you are doing, you are trying to shift the eigenvalues from 2, 5 to -2, -3, and hence you are trying to make the system stable. So you are stabilizing the system. Okay. So let's not go into the stabilizability, just let us talk about the basically the proof of, concerned about the proof of this theorem, which tells that given any set you can find the matrix K such that A plus BK will have eigenvalues equal to that set. Okay. Okay, so now let us go into the proof. So if you want to follow the theorem, it says that it should be controllable. So for that what we need to check is the rank of B comma AB. Okay, and then so it's 2 cross 2, so that's it. So this should be equal to 2. So this is the question, is it true? So let us see. So B is given by 1 comma 1 and A is given by 2 4 0 5. Then AB if we do, so it will be 2 and 4 6, and then sorry, okay, AB 2 4 6, and then you will have 0 5 5. So this is your AB. So this B comma AB, this matrix is given by 1 comma 1 and 6 comma 5. Clearly these are linearly independent, so the rank is equal to 2. So A comma B is a controllable pair or controllable system. Okay, so since it is controllable, we know that such K will exist. Now our goal would be to find that matrix K, right? Okay, so before we move to this, so let me just sketch the idea how to get till that, or maybe just let us directly dive into it. So we will first try to find a vector alpha, okay, using the inverse of this matrix. Where is this matrix? Okay, so we will try to find vector alpha. Okay, so it's basically 1 cross 2 in this particular case. So we'll try to find alpha, which is what we'll do, since it is 2 cross 2 setup, so we'll put 0 1. Okay, if it's n cross n, we'll put 0 0 0 and then 1 at the end point. So this 0 1 times 1 6 1 5 inverse. Okay, so let us try to find the inverse. So 0 1, so determinant is 1 comma 1 upon 5 minus 6, right? So it is -1, the determinant of this matrix. Okay, and then times, so if I try to find the inverse, so it is 5 1 and then -6 -1. So this would be the inverse, and if I do it, so what I get is, so 0 1 would give me this last row, which is 1 -1 when I multiply with -1. So this is my alpha. So now I will try to find this matrix P. So this whole process, where is it? So what we will basically try to do, we will try to deduce this matrix A in a companion form. Okay, and then from there we will get the, or you can directly find, instead of going to companion form, you can, from here also you can get the companion form directly just by finding the eigenvalues, but that will not give me the underlying the matrix P. Okay, so to get that underlying matrix P, so that this P inverse will give me the companion matrix, we are doing this. Okay, so this is alpha, and then the P matrix okay, can be given by this alpha times a. Okay, so alpha is what? Alpha is 1 comma minus 1, and alpha a, if you compute, so 1 comma minus 1 times this a is 2405. So if I do this computation, what I get is, so first row it will get 2, then first row, second column will give me 4 minus, so minus 1, right? So 2 comma minus 1. So this is 2 comma minus 1. So this is the matrix P. Clearly it is invertible. So let us try to find the inverse as well. So inverse would be minus 1 plus 2. So the determinant is 1. Correct. And then this is minus 1, 1, 1, minus 2. So this is the matrix P inverse. Okay, then you can clearly check, okay, that this P inverse will give you, so this 1 minus 1, 2 comma minus 1, and then a was what? 2405, and the P inverse is minus 1, 1, minus 2, 1, right? So if I do this computation, this is 1 minus 1, 2 minus 1. From here you will get 2, 4, minus 10, correct, and then you will have 6, then you have minus 10, you have 5, and then from here you will get 1 minus 1. So this will be 0, this will be 1, this is minus 20, and then plus 10, so minus 10, then you will have 12, minus 5, 7. Okay, so this is the companion form, right? So from here you can clearly guess what will be the coefficient of this characteristic polynomial of A. Okay, so these entries what you see are nothing but the coefficient of the characteristic polynomial of A, and that also you can determine directly. So your A was this. So let us do a bit quick computation. So A minus lambda I, if I do, so what I am getting is 2, 4, 0, 5 minus lambda, 2 minus lambda, and this. So if I do, this is lambda minus 2 and then lambda minus 5, and this is giving me lambda square minus 7 lambda plus 10, right? So this is clearly the negative of these coefficients. And this theorem we have already seen, that this companion matrix, the last row comes from the coefficient. Okay, so looking at this coefficient, okay, so this was just to justify. Okay, so from the coefficient what I can say, but I am assuming this alpha 1 to be minus 7 and alpha 2 to be 10. So I am just taking the coefficient. Okay, so this is alpha 1 and alpha 2. Now I will try to look. So this is something. Okay, so this is, now let us go to, so this was coming from the coefficient of the characteristic polynomial of A, but now we'll try to see what is the characteristic polynomial of our desired matrix. So the characteristic polynomial, okay, of A plus BK, what do you want, right? Because this is in our hands. So this what we want is, so the eigenvalues what we wanted were minus 2 and minus 3. So the characteristic polynomial would be lambda plus 2, lambda plus 3, and this would give you lambda square minus plus 5 lambda plus 6. So over here I am naming this beta 1 to be 5 and beta 2 to be 6. Okay, so these are the coefficients 5 and 6. Now what you define? You define the gamma I, which is nothing but alpha I minus beta I. So then you will get gamma 1, which is given by alpha 1 is minus 7 and then minus 5, so minus 12, and beta 2 is 10 minus 6, so this is 4. Sorry, this is gamma 2. Okay, now using these gamma i's, you define a matrix C, okay, or whatever you call. So C would be nothing but you take this gamma 2 and then gamma 1 and then multiply with P. So this is the use of this matrix. I mean, why we did all this to get the companion matrix, because I wanted this P. What is the underlying P? Otherwise, I can directly, using this information from here only, I can say that there exists P such that P inverse AP would be this canonical form. But why we did this? Because just using the eigenvalues we can say this, but we did this just to get the expression of P. Okay, so this P, now you can write this is gamma 2 is 4 and then minus 12, and then you have this matrix P. So P is 1 minus 1, 2 minus 1. Now if you do the multiplication, you can clearly see it is 4 minus 24, which is minus 20, and then minus 4 plus 12, 8. So this is the matrix C what we have got. Now from here you can directly compute what will be, okay, so this is not C, this is the K, what I mean, the matrix K, what we wanted. Okay, now you can see that this, the resulting system, okay, so now my control would be K times YT, and that is my UT is given by, so minus 20 Y1 plus 8 Y2. So with T. So this is the expression of the control. So this UT. Okay, so we have found UT as this. Let me write it small. So this is the control, that what we wanted. Now let us verify this. Okay, so for verification, so basically what we want to see, so now our conclusion is that this control, this feedback control will give me the desired eigenvalue. Okay, so that means this A plus BK matrix, the eigenvalues of is equal to, what was that, minus 2 and minus 3. So this is what we want to verify. So A plus BK is given by, so A was 2405, B is 1, 1, 1, 1, and your K is minus 28. So if I do this 2405, this would give me minus 28 minus 28 plus so this is 18, this is 12 minus 20, 13, right? Now let us try to check this eigenvalue. So lambda minus, or A plus BK minus lambda I would do, so minus, sorry, 18 minus lambda, 12 minus 20, 13 minus lambda. So this is nothing but 18 minus lambda, 13 minus lambda, and then minus or plus, so it will be 240, correct?
It is minus 18, right? First row, first column.
Oh, it is minus 18, correct. Yeah, thanks. So minus 18. Okay, so now if I multiply, I'll get lambda square, and then minus 13 lambda, and then minus plus 18. So 18 minus 13 would give me plus 5 lambda, and then I will have here minus 18. So let us do the computations. So 18 into 13 if I do, so 234 plus 240. So this will give me lambda square plus 5 lambda, and then plus 6, right? And this is what we got here. So this I can write it as So this is nothing but lambda plus 2 lambda plus 3. Okay, and hence it verifies the thing, right? So this is the process. So what you need to do is basically the first step should be that okay, we need to verify this thing, that it is controllable or not. This is the first step. The second step is to find this vector alpha, okay, 1 cross 2 vector. Then what we did, just define the p. So this step is basically, this one is basically to get the matrix p, so that which gives you the companion matrix. Okay, once you got the information of p, then you got the information. Okay, so this will come from the companion matrix, and that is easy to compute anyway directly. So just looking at the eigen, so just compute this. You don't even need to bother about this thing. You just compute the eigenvalues from here, the characteristic polynomial. Then this just write the first coefficient is alpha 1, the second one is alpha 2. Then you compute what you want. Okay, so beta 1 is 5, beta 2 is 6. Now just subtract it. Okay, so just subtract it here, and then you got this k, which is this one, just gamma 2 times gamma 1 times the matrix p. Okay, so this is the only thing that you need to basically remember, that the k has this form. Okay, and then you are done. This is your k, and hence you got the u. Okay, so this was the case when m was 1, that u b was just a vector in Rn. Okay, so this is the case when m is equal to 1. So is it possible for any m? And this is what the question was initially. To get the stabilizability, it's not always that the control operator or the control matrix B will have m equals to 1. That is not true. It's not always true. So this is the general setup. So you suppose this kind of system, which is general one, n cross n, n cross m. Okay, then also the theorem is true. So if you have any set of eigenvalues, okay, then there will exist so if again the condition is that the AB should be controllable. Okay, so assume this AB is controllable, then there exists the matrix K, m cross n, such that the eigenvalues of A plus BK is set S. Okay, so the same theorem holds here as well. The proof of this theorem is basically what you do. So I think I must have written. Yeah, okay. So we'll come to the proof. Okay. So okay, we'll see why. So I mean from here basically you will have to deduce to the case m equal to 1. Okay. I mean you write this system as some y prime equal to a plus bk1 times u plus again some b1 v. This kind of, so basically from here you try to get this kind of system, and then you use the proof. Okay, so from the last step you know that such v exists. Okay, so here it's y. So from the last theorem you know that such b1 will exist. I mean you can find v such that this a plus bk1 plus b1 k2 will have desired eigenvalue. Now using this k1 and k2 you can define this k. Okay, so this b tilde or a plus such that a plus bk will be equal to, I mean the eigenvalues of this will be given by this. Okay, so we'll see maybe in the problem or example what I'll discuss, it would be much more clear, but I will state what is the idea, the how, why we are doing it just for m equal to 1 and then we are taking general m, because using m equal to 1 case we can prove this one. Okay, so let us go into the problem first. So this is the problem. The question is that suppose you have this kind of control system. Now the question is for what values of alpha, okay, given any set you can have a resulting control which such that a plus bk, that feedback control, such that a plus bk will have the eigenvalues equal to the set S. Okay, so basically what you need to check is that this system is controllable. Once this system is controllable, you are done. When it is controllable, such existence of feedback control is guaranteed by the pole shifting theorem, right? So let us try to see that what values of alpha it can accept. Okay, so here A is, so we just need to check that the Kalman condition is satisfied. So it is 1 0 1, 1 minus 1 minus 1, 0 0 1. This is your A, and B is given by 1 0 minus alpha. Okay, so now let us try to calculate what is this AB, and then we'll see A square B. Okay, so let us see. So AB is just, it is 1 minus alpha. Second row, when it multiplies, it gives me 1 plus alpha, and then you have minus alpha. Let us calculate what is A square. So A square, if we do, it will be 1 1 0 1 will give me 0, 1 0 1 will give me 2, and then you will have a second row with first column will give you 0, and then you will have 1, and then you will have 1 1 2, so it will be 1, so it will be 0 0 1. I hope I'm not incorrect. Okay, so then from here you can compute what is A square B. So A square B would be 1 minus 2 alpha, and then you will have 1 minus alpha, and then you will have minus alpha. Okay, so this is A square B. So now you can write the matrix, Kalman matrix K as, okay, let me not write K. No. So B, AB, A square B, this is given by 1 0 minus alpha, then you have 1 minus alpha, 1 plus alpha minus alpha, and then you have 1 minus 2 alpha, and then you have minus alpha minus alpha. Okay, so now we have to check whether it has full rank or not. Okay, so for what values of alpha it will have full rank. So let us check the determinant. So determinant of BAB, A square B, is given by, so let us expand along the first column. So 1, it will be minus alpha times 1 plus alpha, and then minus alpha square, then you have minus alpha, it is minus alpha 1 minus alpha minus 1 plus alpha 1 minus 2 alpha. Okay, so which is minus 2 alpha square, then you have minus alpha minus alpha, then it will be minus alpha plus alpha square, then minus 1 plus alpha minus alpha, then it will be plus, and then you will have plus 2 alpha square. I don't know I'm doing correct or not. Okay, let's see. Then what you have is, so minus 2 alpha squares, and then you have, so this will give me, okay, so this alpha cancels with this alpha, then you have 3 alpha square 3 alpha square times minus 2 alpha square minus alpha minus 3 alpha square, and then you have plus alpha. So again this cancels, so you have minus 5 alpha square. And I think I've done some mistake, because just a second. So you have so expanding along the first column, so it's 1 times minus alpha 1 minus alpha square, then minus alpha times 1 minus alpha minus 1 minus 2 alpha, correct? So you have minus alpha minus 2 alpha square minus alpha plus alpha square minus 1 minus 2 alpha plus alpha minus alpha plus alpha. It seems to be correct. There is no alpha cube. Oh, sorry, I got it. Alpha cube, correct. So what I have written here is, where is the mistake? So the mistake is here. So it will be minus 3 alpha cube. Yeah, correct. So now I will have minus, you can take outside. So minus alpha square I can take outside, and then I will have 3 alpha minus 2, correct. So this determinant or the rank of this, so let me write in the next page. So rank of this matrix B A B A square B is full, that is it is 3 if and only if the determinant of this matrix is equal non-zero, which is equivalent to telling that this expression, which is, I hope it's correct, I don't know, again I have doubt, but let us assume whatever it comes, minus alpha square 3 alpha minus 2, this should be non-zero. This is if and only if alpha is non-zero or alpha is not equal to 2 by 3. Okay, so if such things happen, right, then you say that this finding such k can be possible. Okay, so the conclusion is that finding desired k is possible if k belongs to the or alpha, if alpha belongs to r minus 0 comma 2 by 3. If such thing happen, if alpha belong to outside this 2 value, then you will have the existence of k. Okay, so this was an easy check. Okay, so now how the control, so this theorem, how to prove this theorem. So in the proof, what one usually uses is this one, that you find some matrix k1 m cross n, okay, such that you reduce this given system. I mean, okay, it's not reduction basically. So what you basically do, you find one k1, okay, such that the system y prime equals to ay plus bu, you write this system in this way. Okay, so you get a system of this kind, find the matrix k1. Okay, so basically what you are doing here, you are just shifting. So this m was n cross m matrix, now this has gone in this expression. So now the control is this v, and this b1 is some in n cross 1. So this is the change, that the control operator has now changed. So you are considering this control operator. Okay, so instead of considering this system, so it's not that you are not, so I think this convert is wrong word over here. So basically I should not write, so basically so consider this system basically. Okay, I don't know. So basically you want to consider this kind of system. Okay, or you convert is fine, because you convert this. Okay, so this, you get this kind of system. Now the system, this control system, so let this call this a plus bk1 as some other, by some other notation, a tilde. So this is something what we have already seen for m equal to 1. Now using that theory, m equal to 1, you can find the matrix k2, okay, or k2 tilde in this m1 cross n, such that this matrix will have desired eigenvalues. Okay, now recall that what we wanted is we wanted a plus bk kind of thing, and not this kind of matrix expression, right? So now basically you want to convert this one, so that this whole thing you can write it as b times something. Okay, so you can write this b times k2. If you can write this b1 k2, then from here you can clearly say that a plus b, and then you can write k1 plus k2, and then you are done. You get this kind of expression. So now you can define this k. So you got this k2 tilde. Using this k2 tilde, you can define k2 as the first block to be k2 tilde, okay, or just first row, because k2 tilde is 1 cross n matrix. So this is one row, and then the next rows are 0 rows. Okay, you define k2 as this, then you can see that a plus bk is a plus bk1 plus bk2, and this bk2 is nothing but b1 k2 tilde. So b1 is basically the first column of the matrix B. Okay, so this is done in this step. So once you can clearly see, once you reach till here, once you find this k1, then you are done. Okay, because finding k is just using the previous steps to get k2, right? What we did using companion and all those stuffs, and then you just add k1 and k2. I mean, after defining k2 like this, and then you get the k. Okay. Okay, so again, now the question is, we know this step, that in this step we can find this k2 tilde. Okay, the way we just saw. Now the question is how to find this k1, how to get this kind of system. Okay, so this reduction we'll see in example. Okay.
Now here, what is the need of this form? Because earlier itself
This
a
form.
plus b we could able to find the k, right?
Which step you are saying?
No, previous thing. A plus bk. Still we could able to find the k, right? Here why we have added additional plus b1b to this particular format?
I couldn't get. Can you repeat?
Am I audible to you?
Yeah, you are audible.
Yeah.
Can you repeat the question?
No, here you have written y dash of t equal to a plus b k1.
Correct.
Y of t plus b1b.
Okay, so you are asking why we did this?
Yeah, why? What is the need of this form?
Okay, see.
Because if we have multiple, it is more than 1 by n cross 1, then we should go to this form.
No. Why I have gone to this form? See, earlier our system was this. Correct? Now this matrix A is n cross n, this B is n cross m. Okay, and this is a vector in Rm. Okay?
Yeah.
Now what we have done, we have somehow splitted the control. Okay? So basically from here we are writing this system. So okay, just mention this, I mean notice this 2 points. Over here you can see that this is playing the role of A, I mean A plus bk1. Look at this one. This part is telling you that this control, so now this is the control B. Okay, this is the state, right? So in this case your b1 over here is a vector in Rn. So now here m is equal to 1 for this control system. So if I want to write something about this control system, so over here this n is equal to the n, I mean n is as it is, okay, but m is 1, right?
So it is a single column vector.
This b1 is a column. This is the first column of this matrix B.
Okay.
Okay. So you can see now it has reduced to m equal to 1 case, and the earlier pole. So what I was saying, that the earlier case, the pole shifting theorem, what we saw, that was for m equal to 1 case, the proof what we did. So now you can use the same proof to get this part. So the main goal was that reducing this main control system in this form, okay, in this form, this one, so that I can use the previous result. Okay.
That's what I asked, whether it is because for m equal to 1 only we can use the earlier pole placement theorem.
No. See, No, basically the pole shifting theorem is true for any m. Okay. So
Okay.
let me tell you. I think there's some confusion. So this is the main theorem. Okay.
Yeah.
Now what I am saying that this, suppose this theorem has been splitted, the proof. So the proof of this theorem, like split the case when m is equal to 1, you prove it. Now for general m, you use this part to conclude.
Okay.
This we do many times, right?
Yeah, I understood.
Okay. So this general theorem can be proved following these 3 steps. Okay. So now the goal is how to find this, get this matrix K1. Once we get this K1, then this getting K2 is just like the earlier one. So find the companion matrix, get alpha i's, get beta i's, and then you define gamma I, then you define the matrix K. Right? So that's the thing. So this step 2 is fine. So now we'll see some examples where how to find this K1. Okay, the matrix K1. Okay. So remember, this K1 is the first step where we transform the given system in this one with m equal to 1 case. Okay, so let us look at this example. So over here, this is n is equal to 3 and m is equal to 2. Okay. So now here the question is that find the matrix K. Okay. So here it should be K1. Okay. Find K1 for this matrix so that you can whatever I just mentioned, you get that kind of form. It's lightning, I don't know. Okay, so let us try to find this K1 matrix over here. Okay. So again, though it's basically from the proof we are writing this, how to get this matrix K1 for this particular system. So I am not giving the proof, but this is something which comes from the proof. Okay, this is how we prove it. So this is a particular case of the proof. So the first step, obviously, it would be that you check the controllability condition. If it is there, then only you can proceed further. But it's not always the case. Okay, so I'll give an example where that controllability condition does not hold, but still you can find the matrix K. Okay, so you see this theorem. So over here, what our goal is for stabilization, let me repeat it again. So I am saying that suppose you have this kind of system. Okay, now you want to, from here you want to find u as ky so that y prime equal to a plus bk. This system is stable. Okay, this is your goal, right? And you are using the pole shifting theorem basically. Now suppose you know the pole shifting theorem, so you have doing this. So this is possible when you know that a b is controllable, right? Using the pole shifting theorem you can conclude this. Okay. Now the question is, the converse is not true, that going, if AB is controllable, you have this kind of condition, but the reverse is not true. So suppose AB is not controllable. Okay, then you cannot say that the resulting system, you cannot get such resulting system, that you cannot stabilize it. That is not true. Okay, so we'll see some example. Okay. So see here, moreover what we are getting, due to this controllability condition, I am getting a stability with any decay rate. That is the advantage. So you are getting with any decay rate, and that is possible, I mean, when it's controllable. So what example I will show, I will not show that it is stable with any decay rate. Okay. Okay, so anyway, so that was just a remark over here. So over here, our first step is to check that AB is controllable or not. Okay, so let us check. So A is 1 minus 1 0 0 1 minus 1 1 1 2, and B is 0 1 1 1 2 1. Okay, so then you can compute this matrix BAB. Okay, let's compute AB. So AB is first row, then you do the minus 1, 0, then you have minus 1, 0, 5, and then you have 6. What I hope I'm doing correct. Sorry, it would be 4. Okay, so this is AB. So I can write this matrix BA. So let us check this BAB first. Yeah, I mean these two rows are clearly linearly independent. So I can say that the columns of B are Li. Okay. So now let us look at this. So anyway, the rank is somehow it's minimum 2. That is clear. Now we want whether it is 3 or not. So it is 0, 1, 2, 1, 1, 1, and then you have minus 1, minus 1, 5, and then you have 0, 0, 4. You can clearly see. Okay, so best example is to consider this one. Okay, so now if you consider the determinant of this matrix, right, so you see that if you expand it from 4, it will be 0, minus 1, which is non-zero. So clearly these three columns are alike. I mean this could also be, I'm not saying that this is not, but this is easier to check, so that's why I'm writing. These three columns are Li, and hence you can clearly see that the rank is 3. So rank of this B, AB, A square B is equal to 3. Okay. So controllable. So this implies A comma B is controllable. Okay. So now let us go to the step 2. Okay. So step 2 is basically the main step where we want to do the conversion. Okay. So for that, first, I mean in this one, first to do. Okay, or let me write step 2 as construction of M. Construction of, so I will tell what this, how this matrix is constructed. So M is basically what you do. So it is constructed using this kind of formula. So you use B1, the first column of the matrix B, then you compute A B1, okay, and if this B1 and A B1 are linearly independent, you put it here. You keep on going to do this, so you will get A R1 minus 1 B1. So at some point you compute what highest power you can reach, so that all these are linearly independent. Now suppose this, so this is basically the columns of this matrix. Okay, so this matrix, so you are trying to put the columns of this matrix. You know that the rank is 3, so you will get at most 3. Okay, in case of n dimension you will get n. So you just choose like this. The moment you get that these are linearly dependent, I mean, so obviously we are putting it here so that A R1 B is Li to the, or it is depending. So how should I write? So A R minus 1 B depends on the previous one. Okay, then you put B2. You do the same thing with B2. So you again take A B2 like this. Okay, till A R2 minus 1 B2 like this, and then again you choose B3. So I mean you will get it, it will end finitely, because you know that the rank is going to be 3, so you will get maximum 3 columns. In this case, in n dimension you will get n columns. Okay. Okay, so let us try to compute what is M here. So M is the first B1. Okay, so B1 over here what we are choosing is non-zero. That is, we are assuming without loss of generality that B is non-zero, and the first column. Otherwise you just shift the columns, that's it. Okay, so the M would be the first column of B. So the first column of B is 0, 1, 2. So put it here 0, 1, 2. Now let us try to compute A times B1. Okay, so let us compute here A times B1. So the first row of A with first, I mean obviously, so maybe I should write A times, writing 0, 1, 2. So you will get here 1 minus 1, so it will get minus 1. In the second row it will get minus 1, right? and then third you will get 5, right? So this is minus 1 minus 1. Okay, so over here note that these two are linearly independent, so these are a line. Okay, now the next step would be to take again power a square b1. Okay, so for that we'll have to compute a square. So just compute a square somewhere here. So a square is just square of this term. So square of this matrix, so it is 1 minus 1 0, so if I multiply, so 1, again the first row with the second column, so 1 minus 1 0, sorry, so 1, it will be minus 2, then 1 minus 1 0 will give you 1, this will give you minus 1, this will give you 0, this will give you minus 1 minus 2 minus 3, so this will give you 1 1 2 will give you 3, 1 1 2 will give you 2, 2 will give you 4 minus 1 3. I hope it's correct. Then you compute a square b1, a square times what is b1, 0 1 2. If we compute this one, what I get is, so first row is minus 2 and then 2 it is 0, then you will have minus 6 and okay just a second, 0 0 minus 6, then you have 3 2 8, 0 minus 6 8. So now you just put it here and then you check. Okay, so first let us check that whether this is linearly independent to this or not. So let us check the determinant. So from here let us check the determinant of 0 1 2 minus 1 minus 1 5 and then 0 minus 6 8. Okay, so if I expand along the first row, what I get is 1 times 8 minus 12, which is 12, which is non-zero, right? So this is non-zero, so it is linearly independent to the other two vectors. So I can put it here, 0 minus 6 8. So this is my m. Okay, so how I compute m I just mentioned like this. Okay, now you have to compute what is its inverse.
Okay, here suppose b1 and ab1 are linearly not linearly independent. Correct. Then you have to put b2, right?
Correct, then I will put b2 over here.
Then b2 here.
So first I will put b1. Suppose ab1 is not li. Okay, then I will put b2. Okay, and suppose again I will put ab2. Okay, if it is not linearly independent, okay, suppose it is LD, then I will put a square b1 b2, but obviously I'll get 3 because I know that the rank of this matrix is 3, so I'll get 3 for sure.
Okay.
Yeah. So you see this b ab a square b is nothing but this is b1 b2 a b1 a b2 a square b1 a square b2, right? Where bi's are the columns of matrix B. Then obviously this rank is 3, that means I can get 3, but I have chosen this fashion what I mentioned here to get this desired matrix M. Okay, so now once I get this M, so now I'll compute the inverse. Okay, because it will be used. Okay, so okay, let us not compute now, so we'll compute. So now I define what is this matrix N. Okay, so this is, let me say this is step 3. Step 3 is construction of N. Okay, and this M, you see this M is N cross N matrix. Let me mention it here. This is N cross N, and over here this N would be M cross N. Okay, and how it is constructed. So it is constructed on how you are choosing this M. Okay, so first thing is that suppose over here what is my R1. Okay, R1 is the highest power, so R1 minus 1 is highest power of A such that A raised to the power that power such that A R1 minus 1 times B1 is Li to A K B1, where K is less than R1 minus 1. So this is the definition, right? R1 minus 1. This is how R1 is defined, right? So over here you see this R1 minus 1 is 2 because this is my B1. Okay, let me use some other color. So this is my B1, this is A B1, this is A square B1. So here R1 minus 1 is 2, that means R1 is equal to 3. Okay, and how you construct this N is like this. So what you do, so this is I am taking for the general thing. So whatever R1 you get, okay, so I will get R1 as something. So R1 at R1 1, so I'll put my E2. Okay, so this N, you recall that this is M cross N matrix. Let me take a bit farther. This is M cross N. So all the columns is a vector in Rm. So what you do at R1th row, okay, you put E2. E2 means E2 would be 0, 1, 0, dot dot dot, which is a vector in Rm. Okay, and the rest is 0. Then at R2 again, what you do at R2 you again put this E3. Okay, and then you proceed in the same fashion. Okay, in this case we just have to stop till R1. Okay, so in this case, because you see this R1 over here I got 3, so I don't have to go beyond that. But in general there is a process you can go in this fashion. Okay, so over here this matrix N, what I will compute is R1 is 3, so the third column, so this is first column, second column, third column. At third column I will put E2. So over here you see where is M. So over here you see this is M is 2, right? M is 2. So this matrix N is 2 cross 3 matrix. Okay, and in the first two columns it will be 0, and in third column I'll put E1. So in this column I'll put E1, which is 0, 1, sorry, this is E2, 0, 1, or in column form it is 0, 1, 0. So over here it's 0, 1, now there is no place to 0, so I'll put 0, 1, that's it. So this is how you can construct this N. Okay, now the final step would be,
in this same case for B1, AB1 is dependent, then how this N will be, can you just
sorry I couldn't get.
No, in this case suppose B1 and AB1 are linearly dependent.
Oh, okay, so
in
when
that case, how it,
yeah, so see, if this is depending on B1, so suppose this kind of configuration, B1 and then you put B2 and then AB2, right? So over here what is R1? R1 is 1, 1 or correct, R1 is 1, right? Because A raised to the power 0 times B1 is the maximum linearly independent thing, right? So here R1 minus 1 is 0, so R1 is 1. In that situation this N, I'll put E1, so E1 is 0, 1, 0, so I have 2 cross 2, so it's gone, it's 2 cross 3, so I'll put E2 over there, E2, so this is E2, right? Now what is my R2? R2, if I compute, R2 would be 2, right? R2 is the over here, so R2 minus 1, if I compute it is 1, which implies R2 is this 2, right? So in the second column I'll put E3, which is E3 is 0, 1, 0, so I'll put 0, 0, 0, 1, so I'll get 0, 0, this kind of thing. Okay, and then third column would be 0 0, I guess. Just a second. This is first would be okay, R1 I'll put. So at RI position you have to put EI, not EI but EI plus 1. Okay, and the rest of the places are 0 basically.
Okay. That means here there is no R2, right? No, in this case there is no R2, right? Only up to we have R1 equal to 1.
No, R2 is there, right? Okay, in this case, okay, in our case, yeah, R2 is not there.
Yeah. Oh, okay. So correct. It will be 0, 0, 0, 0, 0.
Yeah, in our case it's just 0, 0, 0, 0 and then 0, 1 at last. The other way, I mean, what you have saying, I think this would be the matrix N. Okay. Now finally, the matrix K, they can put here. So finally, you can compute what is step 4 is getting K1, which is given by N times M inverse. Okay, so N is, so you see this N is 2 cross 3 cross 2. Sorry, N is 2 cross 3 and this is 3 cross 3. So you'll get 2 cross 3 matrix, and which is what we want, so that I can do BK. So BK was 3 cross 2 and this is 2 cross 3. Okay, so order are, I mean, the order is conserved, so there is no issue in the order. Okay, so we get this kind of thing. So this is how we compute K1. So for K1, let us just substitute what is N and M inverse. So N is just 0, 0, 0, 0 and then 0, 1. And M inverse, so what was M? So M was this matrix. So inverse of this matrix. Okay. So now you can, let us compute what is the inverse. So let us first compute the determinant. So you can see the determinant is 1. Then along the first row, and then it's 8 minus 12, which is plus 12, which is 20. So you write 1 upon 20. You just compute the adjoints, so you'll get minus 8 and plus 30, right? Minus 8 plus 30, which is 22. And then over here you get 8 minus 12, which is 20, so you'll get minus 20, and then if you go this 5 plus 2 7, so you'll get 7. Okay, so you just do the computation maybe. Okay, here whatever you get, then you take the transpose, so you will get the inverse, and this is how you get K1. So K1 is just N times M inverse. Okay, so the main thing is to find this M and N, that's it. So now you get this K1, so that means from here you got this kind of system, BK1Y plus B1 times B, where B1 is this one. So what was B1? So B1 is what is B1? 0 1 2, 0 1 2, and then you find what is U2. Okay, so now do you know the earlier theory, what I did just before, finding companion matrix P, then you compute alpha I, beta I, subtract it to get gamma I, then you write the this matrix K, right? So using that you can get this K2, and then you can get K by getting, I mean, from K1 and K2. Okay. Okay, so I mean the question was just still here that you have to find the matrix K1. Okay, but to find K2, you can use the method what I just stated over here. This one. So till here we did for that example. This is something that we can do using the first example what we saw, the case m equal to 1, and then you can define this k2, and then finally k would be k1 plus k2. Okay. Okay, so that's all for this problem. Now let us move to another this concept. Okay, so this is like when you know that okay, the system is not controllable. Okay, then what can you do? Okay, in some cases you can actually give some result of a stability. Okay, how you can do that? Suppose you have this matrix, I mean this system. Suppose the rank of this matrix is L, I mean it is strictly less than N. Then you can decompose the matrix A in this form, in upper triangular block kind of form. So over here you have the 0 and the rest whatever it is you don't care. Okay, and if when you do this kind of thing, I mean when you do the conversion, you will get the B instead of B, you will get this kind of expression. Okay, so the resulting system, okay, so I mean this system can be converted in this form. Okay, so PB times again P inverse U tilde will be the new control, something like that. Not P inverse, but okay, you don't need to go for that inverse. So from here you can write this as Y tilde prime, okay, is equal to this. Let's say this is A tilde. So A tilde Y tilde. No, A tilde Y. I think Y would be same. Okay, what? Let's not go into this. But okay, you will have this kind of system where generally let's write in Z. So Z prime would be A11, A12, 0, A22, Z plus this B10, and then you will have U. Okay, this kind of system. You can from here you can go here. Okay, in this kind of scenario. Okay, so you notice over here that okay, so let me first write it in further. So I'm writing Z as Z1, so Z I'm writing as Z1, Z2, where Z1 is in RL and this is in Rn minus L. Okay, so this would be A11 Z1 plus A12 Z2, and this would be A22 Z2, and okay, with control, so with control it would be plus B1U. Okay, so now you see, suppose this system, if you consider just this I mean I should use some other notation, maybe W prime equal to A22 W you consider. Now suppose this is stable. Okay, assume that all the eigenvalues of A22 are negative. Okay, you can also see from here the eigenvalues of this would be nothing but the eigenvalues of A11 and A22. So suppose the eigenvalues of A22 are negative, that means this system is stable. Now you just substitute this over here, this Z2, put the value of Z2. Now you have some system this kind of, where W prime is A11, or let me write the proper system, Z1 prime is A11 Z1 plus B1U and then something FT. FT is this 812 Z2, which is known to you. Okay, now the question is again to find this U so that this whole thing will be stable. So basically you want to shift the eigenvalues of A11. Okay, over here I mean, so instead of F22 I should write, let's not write FT, I should write A12 Z2 only. Okay, but Z2 is known to you here. Okay, now the goal would be to find this U in terms of Y1 and Z1 and Z2, so that this resulting system will be stable. Okay, that is the question. So if this Z2 component is stable, and if you can stabilize this one, then you are done. The whole system would be stable. Okay, is it possible? I don't know. It should be, yeah. So the whole system would be stable. Okay, so if the second component is stable, and you know that the, okay, so when I write this theorem I should mention this as well, that this, when you write decompose this kind of system in this form, okay, when you decompose it, then this a11 b1 pair is controllable. Okay, so you can, when the rank is L, then you can decompose in this kind, so that this a11 b1 is controllable. So now you can use the earlier theory that a11 b1 is controllable, then you can find u in the feedback form, so that everything goes well. Okay, so now you cannot do this anything with this, the second component, okay, or this z2 over here, but you can do something for this part. So when it's partially controllable, you can just, I mean, do some changes in the that part where the control is acting. The second part you have no control, and so you cannot do anything. I mean, you cannot change the stability property just because control is not acting there. Okay, so in this some partial case, you can just concentrate on this block. Okay, and you can find the feedback control when you restrict your study to just this pair. Okay, you forget about the second component, and in the case second component is stable, you can say the whole system is stable or not. You can guarantee that. Okay. Okay, so this was about partially controllable system. Okay, and this is what I have written probably. Okay, so what I just said, I have written it here. Okay, now let us come to this question. So over here, what I was telling you earlier. Okay, so let me write this system. So you see here, let us check the controllability condition. So here A is this 1 0 0 0 2 0 0 0 minus 3, and B is 1 0 0 0 1 0. Okay, so this you check that the rank of B, AB, A square B is not going to be 3, it's equal to 2, which is strictly less than 3, and I can guarantee this by looking at this system itself. You see, if I write this system, so what is this y prime t is equal to this y1 t plus u1 t, and then you have 2 y1 t plus y2 u2 t, and then you have minus 3 y3 t, right? So you can clearly see that in this one you have no control, right? In the third component there is no coupling also, so you cannot expect controllability, that is obvious. So that's why I can say that the rank is less than 3. In fact, if you calculate, you will get the rank is 2. Okay, and that is also somewhere related to that you have two controls to control the first two components. Okay, so you can clearly see that A comma B is not controllable. Okay, but the question what I am asking is the system stabilizable? Okay, I know it is not controllable. Okay, stabilizability also I am not asking. So okay, I can ask stabilizable. In so the more precise question is this one. So I should not write it in this fashion. The more precise question is, can we find feedback control u such that u equals like this ky, such that a plus bk, eigenvalues of a plus bk is equal to minus 1, minus 2, minus 3. Okay, now once I get this eigenvalue, I can say that a plus bk is stable. Okay, and the decay rate would be, that we'll see what will be the decay rate. So it's clear that it is greater than minus 1. So omega is greater than minus 1. I think here it would be equal. Let's see, because it's diagonal case, so I am expecting that. Okay, so here omega, the decay rate is equal to minus 1, I guess. So the best you can get is minus 1. Okay. Okay, so now let us try to answer this. Okay, so just a second. Okay, so we cannot use the earlier theorem, right? Because it's not controllable, so we cannot use the earlier theorem, and hence we cannot go in that process. But how do we find this matrix K? Okay, so let us just look at this system. So let me just copy this. So let us try to understand this. Because I mean it's easy to see over here. Okay, so my goal is what? I want my system y prime in this form. That you see, I want the system to have the eigenvalues -1, -2, right? So my a plus, so -1, -2, -3. So -3 is always there, is already there, right? So eigenvalues. So these two eigenvalues what I have, 1 and 2, I want to shift it to -1, -2. Basically I just want to shift these two eigenvalues, and that's why I have put the control u1 and u2 on just these two components, you see, because this is fine. I don't want to change this one. If I put here -4, I'll have to take u3 as well. Okay, but then the question is how to, what aim you should choose. Okay, that's it. So for if you want to change this also -3 to -5, then I'll have to go for u3. It might be possible just with two not with these two controls for sure. Okay, so you'll have to choose another control u3. Okay, in this particular case. Okay. With this operator, so this b operator is playing very important role over here. Okay, so we have this system, then we want to shift these two to the negative side. So it is 1, so I want to go, so this is 1 and 2. So you see in the real line. So let's forget about -3, because I cannot control, I cannot change this, so let's not talk about that. And this is not also what we would like to, because I know that -3 is already eigenvalue of this one. So this is fine, this is done. We just have to bring these 1 and 2 to -1, -2. So I have 1 here and 2 here, and what I want is -1, -2, right? So if I choose my u1, so it depends, right? So I mean, how should I say? So either you can, so there are two possibilities. Let me explain it here. So possibility 1 is that you bring this here and this here, right? So in this case u1, because y1 I want, so u1 would be -2 y1, right? Because I am shifting by 2 units, and here u2 would be -4 I'll have to do, right? So -4 y2. The other possibility is that I shift this here and I shift this here, right? So in this case this is my u1, so I am shifting 1 to -2, so I am shifting by 3 units. So u1 would be -3 y1. Here again I am shifting by 3 units, so here u2 would be -3 y2. So let me just copy it there. Okay, so this is the picture. Right? And then in these two cases you can clearly see that I am not able to get this controllability, but I can get stabilizability using this kind of controls. So this is maybe case 1, or the type 1 of the control, or control 1, control 2, maybe control 1, and this is control 2 in this case, and this is control 2. Okay, so over here we are not getting the controllability, but we can stabilize the system. But note here the fact that okay, here also you can actually completely stabilize the system. Okay, because the maximum value is in your hand. So the maximum decay, I mean the decay you can get whatever you want by changing these two eigenvalues. No, you cannot get any. Okay, so yeah, you can get any. You can get probably any decay rate. Okay, but that's not the question here. Okay, so we were not the system was not controllable, but still we got the stabilizability of the system. Okay, now let us go to this observer thing. Okay, so what is state observer? So suppose you have a observation system. So this is your control system, control equation, and this is the observation with C matrix. Okay, assume that the system is observable. So you know that observability property holds. That means from this zt you can uniquely determine y0 or y0, and that means you can get yt. So the main goal is to get yt. So from zt you can reach yt. That's what observability means. But many of the times you don't have any expression, or you cannot derive this yt easily. You know that it can be done, but it's not always possible, okay, to get the explicit expression of this yt from zt. Okay, so what you do in that case, you do some estimation. Okay, so you define this y hat to be estimate of y. Okay, and how using the estimation is done using the knowledge of z and u. Okay, then you define this z hat, using this estimate you define the observation. So it is, you are estimating the observation using this estimation y hat. Okay, so this is the estimate of observer. Then you define this difference, which is the error basically. Z is the actual observer, z hat is the approximation or estimate of the observer. So you define this difference, okay, as z tilde. Okay, now my goal would be to, when this z tilde goes to 0, or my goal would be to study this, that y tilde t basically goes to 0. That means as t goes to infinity. So in large time this estimation is almost equal to the actual state. Okay, so you are estimating the state initially, but you are saying that can we do this kind of thing, that for, okay, initially it might not be the same, but for large time you know that this y tilde will go to 0. That means this y hat, the estimate, will converge to the actual solution yt. Okay, so this is the concept of this observer, state observer. Okay, so so this is the, so you consider this estimatory equation. Okay, over here this m is not known to you. This a b you know, this y hat is the estimation, ut you know, z tilde is the difference, but the main thing is that m you don't know, and the m is something that you want to find. Okay, so m is n cross q matrix, where q is the number of component of the observation. So the c was q cross n. Okay, so you have this m as this matrix. Then you can see that this y tilde, which is the difference, will satisfy this equation. Now from here you can clearly see that this y tilde will have this kind of expression. Okay, so now the whole theory, now you just focus on this equation in this solution. See this, if a plus mc has negative real values, or if a plus mc is stable, then you can clearly see that, from here you can say that y tilde t goes to 0 as t goes to infinity if a plus mc is stable or has negative eigenvalues, with negative real part. Okay. Now our goal would be to find this m so that this a plus mc has negative real part. So this is something, earlier what we saw is like we were trying to deal with this a plus bk kind of thing, right? There's somewhere the duality problem. You see, this a plus bk is when we were talking about the control problem, but now when we are talking about the observability, when we are observing the things, when we are in observable system, okay, and not the controllable system, we are trying to understand this kind of matrix A plus MC. Okay, now you just do the adjoint kind of thing. So you here, if you take the adjoint or transpose, you will get A star, K star, B star, right? So this is something, you see the comparison. So let us say this is A tilde, M tilde, C tilde. You see this A star, B star. Okay, so this is some sense the duality kind of study. What we studied so far is stabilizing the equation. Now we're doing this kind of study. Okay, so that is dual to this thing. So when the approximation, okay, y hat is converging to the actual what do you say, the actual state. Okay, so that is possible when this, you can do this kind of thing, that A plus MC has negative eigenvalues. Okay, so that is the whole game. Again, the similar, I mean, there is nothing new, the proof is exactly the same, and using the duality relation. Okay, so that's all about this thing. Let us do one problem related to this one. Okay. Okay, so now the question is, this, you have to find a matrix. So you have this control system and the observation is this one. So this is nothing but 1 comma 0 y1 y2 or yt. So this is the matrix C. Okay, observation matrix. So over here the question is that you have to find M, so that A plus MC has eigenvalues -1 and -2. But what we have studied so far, that A plus BK kind of thing, we can do this kind of study. That if A has some matrix, I can shift it using A plus BK. I mean post multiplying the control operator. So here we will do the same thing. So if you know that taking transpose does not change the eigenvalue. So if I take the transpose of this, okay, so let me write in the next page probably. Okay. So eigenvalues of A plus MC is same as eigenvalues of A plus MC transpose or star. So this is nothing but A star plus C star and M star. So you have to find what is M star, right? So let us say this A tilde as A star, and what is that? A star is 0 1 1 2, 0 1 1 2, and your C star, sorry, B tilde, let's write in this fashion. B tilde, which is equal to C star, is 1 0. Okay, so now you see here, now the question is, let me rephrase the question. So the question is find K such that A tilde plus B tilde K has eigenvalues -1 -2, right? And you note here that for this B tilde, this is the case when M is equal to 1, right? This is 2 cross 1 matrix. Right? So now you can follow the first problem. So this kind of problem we already did for some other kind of matrices. So this you can do it by yourself. So this is exercise. Okay, so this you can do just what I mentioned in the, it's one of the problem was dealing with this kind of problem, that you have to find the K, and now you can just put M equals to K star. Once you do this K star business, because you see here this M star and K, so this M is nothing but K star, so the final would be define M as K star, and hence you are done. Okay, so this kind of question, okay, is similar to what we have already seen, and this kind of question, why we need this kind of question, okay, to address this kind of problem, that when you take the approximation, whether this y tilde or the difference or the error that converges to 0 or not. So that can be done by choosing proper C. Okay, choosing proper M. and C is the observability matrix. Sorry, observation matrix. Okay. So the problem is similar, but now this question has changed in a duality form. What earlier question was to find feedback control, over here we are trying to find this matrix same, so that this difference between observation and exact thing goes to 0. Okay, so that's all for today. So do you have any question or doubt? Anything? Okay, if there is no question, let's stop here. Okay, see you next week then.
Okay, thank you.
Bye.